Pliku Aceh is one of the typical foods of Aceh made from coconut pulp, fermented with certain spices. This food has a distinctive taste and is popular among the people of Aceh and tourists. However, in the process of making Pliku Aceh, there are some obstacles faced by the entrepreneurs. One of them is the difficulty in choosing the right coconut to create an optimal mixture. The coconut used to make Pliku Aceh must have certain criteria, namely ripe, semi-ripe, and old. Ripe coconut is used to give a sweet taste, semi-ripe coconut is used to give a sour taste, and old coconut is used to give a savory taste. If the proportion of coconut used is not appropriate, the quality of Pliku Aceh will decrease. Therefore, a method is needed that can help entrepreneurs in classifying coconuts according to the required categories. One of the methods that can be used to classify coconuts is convolutional neural network, CNN, which is a machine learning method that can analyze images by extracting important features from the images. CNN has been widely used for various image classification applications, such as face recognition, object detection, and image segmentation. CNN has some advantages over other image classification methods, such as the ability to learn automatically from data, flexibility in adjusting the architecture, and efficiency in computation. However, CNN also has some challenges, such as requiring a lot of data for training, sensitive to parameters, and prone to overfitting. Therefore, research needs to be done to explore the most suitable CNN architecture for classifying coconuts. Research objectives. To make the research more focused, the authors have set the focus of this research to several points, namely, conducting image acquisition of representative coconuts from one or two locations of image capture, performing image preprocessing to prepare training and testing data, testing the performance of the CNN model in classifying coconut images based on the accuracy metric of classification, providing solutions to help choose the right coconut and improve the quality and quantity of Pliku production. Research benefits providing solutions to overcome the problems in choosing the right coconut to produce quality Pliku and improve production efficiency by using AI technology. Showing the potential use of AI technology, especially CNN, in classifying coconut images, which can be applied to the fields of agriculture and food processing industry. Improving the quality of Pliku production by ensuring the right proportion of ripe, semi-ripe, and old coconuts. CNN, Convolutional Neural Network Method. In 1959, the concept of Gabor filter was introduced by Dennis Gabor, which became the basis of image processing. In 1980, the basic concept of convolutional neural network, CNN, was introduced by Jan LeCun. He introduced a convolutional neural network model known as LeNet-5. In 2012, Alex Krzyzewski won the ImageNet competition by using a larger and deeper convolutional neural network model known as AlexNet. After AlexNet, many other CNN models were developed, such as VGGNet, GoogleNet, and ResNet. This paved the way for great advances in the field of image processing and pattern recognition. In 2015, the convolutional neural network Deep Dream was developed by Google. It allows us to generate synthetic images that are weird and interesting by using gradient optimization techniques. Currently, CNN is used in various applications, such as face recognition, autonomous vehicles, handwriting recognition, and even in video games. One of the common deep learning methods used to process data, images, or videos are convolutional neural network, which is often abbreviated as CNN. CNN is a neuron network that has a convolution layer. Neuron network consists of fully connected layers. What is the difference between fully connected layer and convolution layer? For example, we have an input image with a width of 10 pixels, height 10 pixel, and 3 RGB channels. Fully connected will connect each pixel on image, including from 3 color channels for each output. If we want to have 2 outputs, then the connections will be like this. As the name implies, fully connected input and output are fully connected. Each connection also has a weight or separate parameter for narrowing. The image connection between input and output can be illustrated like this. Whereas the convolution layer only looks at the input locally. Like this, parameters will be shared with other parts of the input. So the calculation process will be like this. We can also have two outputs, like this, with parameters that different from before, but still shared the same for each spatial part of the input. In designing the convolution layer, we need to configure several aspects. Firstly, how local do we want our convolution layer to be? It can be very local, with a size of 1 by 1, like this, or 3 by 3, 5 by 5, and so on. This size is referred to as the kernel size. If the size is the same as the input, then our convolution layer is equivalent to a fully connected layer. Secondly, how far does each kernel want to shift at each step? It's called the stride. Do we want to shift it by 1, 2, and so on? It's important to note that the farther it shifts, the more information from the input is lost. Especially if the kernel size is 1 by 1 and the stride is 2, there will definitely be input that is skipped or not counted. However, the stride is useful, among other things, if we want to reduce computational load. Thirdly, if we observe a convolution layer with a kernel size larger than 1, the output size will be smaller than the input. If we want the output to have the same size, we need to add padding to the input. The size and value of the padding can be set by ourselves. Usually the padding value is filled with 0. For example, for a convolution layer with a kernel size of 3 and a stride of 1, if we want the output to have the same size, we can set the padding size to 1, meaning there is padding with a size of 1 pixel on each side. Case study on research. Stages: data collection, pre-processing, model training, model evaluation. The collected data set consists of 3 categories: semi-mature, mature, and old. After that, pre-processing will be carried out. The first step is resizing. This stage is performed to make the size of the images uniform in each picture. This is done to ensure that each image has the same dimensions, making it easier for the model to process image data. Resizing can also reduce computation time during model training due to smaller data sizes. The second step is normalization. Normalization on the image is done to eliminate differences in intensity scale present in the image. This is done so that the image can have a uniform intensity scale, making it easier for the model to process image data. For more details, refer to the table below. To find the normalization value, the formula is pixel normalized, Casex, pixel, min intensity, max intensity, min intensity. Pixel normalized is the pixel intensity value after normalization. Pixel is the original pixel intensity value. Min intensity is the minimum intensity value in the image. Max intensity is the maximum intensity value in the image. This formula transforms pixel intensity values into a range between 0 and 1. The third step is augmentation. Augmentation on the image is done to increase the number of image data. Augmentation can be done in various ways, such as rotating, reducing, enlarging, or adding noise to the image. With the addition of image data, the model can be more accurate in classifying data. The fourth step is segmentation. The segmentation stage is carried out to separate objects in the image from the background. This is done so that the model can focus more on processing objects in the image. In this stage, the author manually separates the necessary objects from the background. also known as removing the background. In image processing, the pre-processing stage is crucial in preparing data before the classification or object detection process. By conducting pre-processing, the generated data becomes better and of higher quality, thereby improving the model's performance in processing image data. The next stage is model training, basic CNN model. The training and validation accuracy graph in the figure of the basic CNN model indicates that the training process achieved 100% accuracy. However, in the validation process, the accuracy only reached 79%. The training and validation loss graph for the basic CNN model shows that the loss in the training and validation processes does not exhibit a significant difference, indicating the model's stability for the coconut dataset comprising 527 images. VGG16 model. The training and validation accuracy of the VGG16 model shows a notable difference between training and validation accuracy. This suggests a potential issue of overfitting. In the VGG16 model, with the limited amount of data in the coconut dataset, this model does not demonstrate good stability. The training and validation loss of the VGG16 model indicate significant differences between the training and validation processes, further pointing to the presence of overfitting in the model. ResNet50 model. The training and validation of the ResNet50 model show instability in the training and validation process, with significant fluctuations in accuracy percentages during validation. The possibility of overfitting in this model is similar to the VGG16 model, attributed to the use of a limited dataset. Evaluation. Testing using animal datasets. After evaluating the previous test results, it was found that the basic CNN was superior to the basic design layers. Therefore, the researchers decided to use an animal dataset with a larger amount of data, 1472 images, to see the performance of the model with a larger dataset. The following are the evaluation results using animal datasets. By using an animal dataset, it can be seen in figure that the regular CNN model shows an increase in accuracy to 85%. However, the training and validation accuracy graphs show model instability with this dataset. Using the animal dataset, it can be seen in figure that the VGG16 model achieves an accuracy of 91%. The training and validation accuracy graph shows a significant improvement compared to the VGG16 model using the coconut dataset. Using the animal dataset, it can be seen in figure that the ResNet50 model achieves an accuracy of 77%. The accuracy graph above shows an improvement compared to the ResNet50 model, which uses the coconut dataset. After carrying out the testing and evaluation process of the models used in this research, the following results were obtained. The CNN model with the coconut dataset at 100 epochs produces an accuracy of 79%. Meanwhile, on animal datasets, this model achieves an accuracy of 85%. The VGG16 model with the coconut dataset at 100 epochs produces an accuracy of 41%. However, on the animal dataset, the model achieved a very high accuracy of 93%. The ResNet50 model with the coconut dataset at 100 epochs achieved an accuracy of 56%. Meanwhile, on the animal dataset, this model achieved an accuracy of 79%. Based on the test and evaluation results, it can be concluded that all models, such as basic CNN, VGG16, and ResNet50, show excellent performance. However, it should be noted that performance depends on its use, which must be adjusted to the available dataset. In this case, the basic CNN model with the coconut dataset shows higher accuracy compared to the VGG16 and ResNet50 models. The VGG16 model with animal dataset shows higher accuracy compared to the basic CNN and ResNet50 models. With the results of this research, the initial aim of the research, namely analyzing the performance of the convolutional neural network CNN method in classifying coconuts as raw materials for food in Aceh, has been achieved. The research results show that the conventional CNN model, designed manually, provides optimal performance with the highest accuracy on a coconut dataset of 527 images. Therefore, the basic CNN model is more suitable for use in coconut fruit classification if the training dataset is small, whereas if the dataset is large, a more complex architectural model such as VGG16 has been proven optimal. However, it is important to carry out a careful analysis of the characteristics of the dataset before choosing the right model so that the results obtained can be more optimal.